Welcome to Bridge the Gap, the physics-oriented podcast of the TU Graz,
where we give insight into physical topics and the life of scientists.
So today on our podcast we'll be talking about superconductivity. With us to discuss it, Christoph Heil, professor at Graz University of Technology.
And we also asked a few of our future listeners what they know about superconductivity and its applications. Here are a few of their answers.
Well, the first question was, what are superconductors? I think superconductors are, like the name already states, of course, conducting metals, but they have the special property that they have little to no resistance at all. I'm not 100% sure if you can have really zero resistance with a superconductor, but I know that the resistance is just so low that it's zero, I guess. Of course, it would be ideal to have a superconducting metal at the room temperature and normal pressure, but I don't think it's possible at the moment. And yeah, the second question was what superconductors can be used for. And I think they are mostly used for MRIs in hospitals, because for MRIs you need really powerful magnets. And in order to not waste any energy and heat, you need superconducting metals.
So superconductivity is an effect that takes place when you cool down certain compounds to very, very low temperatures. So state of the art would be, I guess, around 0 degrees Kelvin. And when you do that, the electric resistance of this material goes to 0. So there's actually no resistance left. And that, of course, has many applications, because normally when you have a normal conductor and you pass through an electric current, much of the electric energy gets transformed, gets turned into thermal energy. That means you lose quite a bit of your electric energy. And that means that superconductors are way more efficient because they don't have any thermal losses. Now, also in the back of my head, I've got interesting effects that occur with magnetism when you introduce superconductivity. And I think one is maglev trains, so frictionless magnetic levitation, which could be used for, I guess, very efficient and high-speed public transport.
Superconductors are special materials or alloys that kind of push all of the inner magnetic field to the outside. Yeah, therefore they have basically zero resistance, but superconductors usually need to be extremely cooled down. And that's the challenge with superconductors, to get those cold temperatures. And I think that's also a big point of research, to focus on so-called high temperature superconductors. So what are superconductors used for? For me, as a biomedical engineer, superconductors play a basic role in biomedical imaging. For example, superconductors are a big part of an MRI.
What I know about superconductivity is actually very vague. So I know that some materials will become superconductive when you lower the temperature. And I also learned somewhere in some lecture that there's something called a Cooper pair, where 2 electrons pair up and then something happens and then the whole material becomes superconductive.
So, hello Christoph. Can you please introduce yourself and tell us about your background?
Sure. My name is Christoph Heil and I'm a researcher at the Graz University of Technology. I do most of my research on superconductivity, and we are using computers and numerical methods to find new superconductors and hopefully better ones.
What are superconductors actually used for? What are current applications?
Well, you can find superconductors in almost all applications where you need extremely strong magnetic fields. So, for example, this would be particle accelerators, fusion reactors, but also in your hospitals you have MRI machines, and they use superconducting coils to generate these extremely strong magnetic fields.
And let's assume it was possible to have superconductors at room temperature. What would be possible applications there?
Well, I mean, the applications would basically be everything where you are using normal conductors nowadays. You could use superconductors, and they would be much more efficient because you don't lose any energy to heat.
We got also a comment by one of the students suggesting to replace the electrical grid by superconducting one if there was a room temperature conductor. How far are we from this, and is this even feasible?
No, I think we are quite far from that away still. And I don't think it will be possible or feasible in the near future to replace the whole grid, the whole electrical grid with superconductors. Because, I mean, these materials, they cost money as well to produce, and they are very specialized materials, and I don't think you can replace the whole electrical grid with superconductors. But I think they will be used in very specific areas where it makes a huge difference to have them. And I mean, we are still also far away from actually having a room temperature superconductor.
That sounds cool, but I had the impression we went straight to the point of applications. So for a general audience, how would you describe a superconductor? What a superconductor is exactly, and how would you explain the basic principles?
Yeah, so superconductivity is, in my opinion, one of the most impressive examples of a macroscopic quantum state. Because in a superconductor, in a superconducting material, if you cool it below its so-called critical temperature, all the electrons form a coherent quantum state and they lose all the electric resistivity. So you can conduct electricity without any resistance in that material. And the second hallmark of superconductivity is that the superconductor is a perfect diamagnet. So it pushes out, it expels all the magnetic field from its interior. And these two properties make superconductors so extremely valuable in certain applications, because as they don't have an electric resistance, you can have very large current densities. And if you make a coil out of a superconducting material, a large current means large magnetic fields. And since you can make very, very, very large currents possible in these superconductors, you can get very, very large magnetic fields.
So that's amazing. But maybe a follow-up questions. What's the difference between non-conventional and conventional superconductors? Because most of the times we hear these terms and like it can be puzzling, to figure that out.
Yeah, no, that's a very good question. We refer to conventional superconductors for superconductors that we can describe with the BCS theory. And at its heart, the way it was devised, BCS, or the Badin-Cooper-Schrieffer theory of superconductivity, describes the pairing between two electrons being mediated by a phonon, so by lattice vibrations. In other words, the crystal in which these electrons live vibrates, it creates vibrations, and these vibrations can couple two electrons together. And this is what we call a conventional superconductor or BCS superconductor. On the other hand, a non-conventional superconductor is a superconductor that does not couple through phonons, but through other mechanisms. So, for example, there could be a charge interaction or a spin-spin interaction that creates a positive or an attractive interaction between two electrons.
What makes the non-conventional superconductors so much harder to describe than the conventional ones?
The problem with non-conventional superconductors is that we don't have a microscopic theory yet on how to describe the pairing. So there are several ideas, there are several models, but there is not one nice microscopic quantum theory that can explain how two electrons attract each other in a non-conventional superconductor, like in a conventional superconductor. And this is why we are having problems describing them in theory or with numerics. And it's also why we can't do any predictions on a non-conventional superconductor, whereas we can calculate the TC, so the critical temperature of a conventional superconductor, just based on the information where the atoms are in the crystal.
Oh, so you now mentioned the critical temperature. I think this is an important point because what one would expect was like reducing the temperature would also mean reducing the electric resistivity, because electrons are decrease the chances of electrons of interaction between electrons or something in that direction, right? So you would imagine reducing temperature equals reducing resistivity. But then for superconductors, you have a finite temperature in which the resistivity drops, right? Can you comment on this? Is it also an important aspect, for example?
Yeah, I mean, definitely. So the the critical temperature of superconductors depends very much on the material. So the first superconductors that were found have a very low critical temperature. So we are talking about 4 Kelvin for mercury, for example, 7 Kelvin for lead. Aluminum has a TC of 1 Kelvin. And then the high TC superconductors, like these non-conventional cuprates, you can have TCs of 130 Kelvin. And as you mentioned previously, the resistivity in a metal generally decreases when you decrease temperature. But in a superconductor, this is a phase transition. So you have, if you lower the temperature, there is a sudden drop in the resistivity, and the resistivity really goes to almost zero, or basically being not measurable anymore. So we're talking about extremely, really zero resistivity compared to a normal metal, well, a non-superconducting metal, where resistivity goes down, but it's still very much measurable.
Maybe I have also a follow-up question in the lack of microscopic theories that you mentioned before. So are there any effective theories also, which is the state-of-the-art simulation, for example, for describing like these non-conventional superconductors? Because one way or another, one has to have a way of like boiling it down to simple principles.
Yeah, sure. I mean, there are a lot of theories or models for non-conventional materials also, where it's also discussed how the pairing works for this particular material and so on. The problem is that all these models or theories, they are based on experimental data, which means that you need to know the experimental data first, and then you can see if your theory describes the material correctly. But we don't have a theory yet that would be able to predict the TC of a non-conventional superconductor just based on the atoms, the atomic positions in a crystal. For those non-conventional superconductors, we always need experiments first, and then we can validate our theory for that particular material. And then we see model A, for example, works better than model B. So then if model A, for example, describes spin-spin coupling of the electrons, then you could say, yeah, probably model A works better for this material. But it's at the current level of theory of how we're working, it's not possible to say a priori for a non-conventional superconductor where we just know where the atoms are sitting, which model would describe this material best. And also I want to mention at this point that most of the non-conventional superconductors are strongly correlated materials, which means they are particularly hard to describe numerically. So normal density functional theory usually is not enough to describe the electronic structure correctly. So you need methods that also include correlation effects like either GW or dynamical mean field theory or other local correlation models, for example. And this, of course, makes everything then a lot harder than to go beyond and calculate a TC, for example.
Do you think the first room temperature superconductor will be a conventional or a non-conventional one?
That's a very good question. I think it will be a conventional one, actually. So in the last few years, research has made a huge improvement on superconductors, in particular for the conventional ones, because now we have the methods at hand. We have very efficient codes. We have extremely powerful computers. So we can scan through a huge number or a huge dimension of phase space and search for new superconducting material, which is what we also do in my group. And in the last few years, we have been able to guide experiments to tell them, well, look at those materials, look at those phases, look at those structures. We think they could be very good superconductors. And in fact, many of those have then been found in experiments. So we think that continuing along that path, we are making very good progress.
So this computational guidance in the conventional case gives it an edge in terms of experimental research with respect to non-conventional ones.
Yes, exactly. So, I mean, for these non-conventional ones, there are the cuprates, for example, that have been found in 1986. And there have been a huge increase in TC. So they're currently the highest TC materials at ambient pressure. But since I don't know how many years, there's not been any improvement for those materials. So like 20 or 30 years. Also for the iron-based superconductors, for example, I think they've been investigated intensely around 2008, 2015, and they are still very intensely investigated. But the TCs, again, in the beginning, they increased very much, but since a few years, there's not been a report of any new record TC in iron pnictides. So, yeah, I mean, these, for non-conventional superconductors, you are almost always reliant on experimental findings, so that somebody finds a completely new class of material, and then you can try doping and all your substitutions and all the plays you usually play in order to increase TC or you improve your material. But you need this initial spark of finding this new class of materials first, whereas in conventional superconductors or for conventional superconductors, we could just basically throw the whole periodic table. So we say we want 3 elements. We pick them randomly from the periodic table. We put the atoms randomly into a box. We just relax the whole thing with DFT. We find the ground state structures or the metastable structures. And then for all these structures, we calculate the TC. And then we focus on those materials which have the highest TC. So there's a lot more we can do computationally instead of having to wait for the experiments to show us a new material class first.
So there seems to be a huge gap, in a sense, in between these conventional and non-conventional superconductors, in the sense like that the first, meaning that non-conventional ones, are relying more on experiments, so some really advancement in experiments. And whereas for the other class of materials, you say basically we could, in principle, predict every structure and look at those and then tell the experimentalists, well, go and look for this and this feature. So based on this observation, what do you think the next steps will be, like both in theoretical understanding and experiments, or what do you think it will be?
Yeah, right. So in last few years, the numerical community, they have focused on finding for certain environmental properties like pressure and temperature, the most stable structures, and then predicting a TC of those structures. And the experimentalists have then tried to find those in the lab. I think the research now shifts more to also take into account that you can access metastable states in experiments. And in fact, many of the interesting materials are metastable ones. Think, for example, diamond. Diamond is one of the most famous metastable materials, where the ground state structure, if you just look at the energy, is graphene. But diamond is a very metastable structure. I mean, it exists for thousands of years once you've put it into the structure. And you need a lot of pressure and you need a lot of temperature to get carbon to form a diamond. But once you have it in the diamond structure, it stays there usually. And you can think of it quite similar to what we try to achieve with our research nowadays. So we try to see not only which states are thermodynamically the most stable, but we also try to look at metastable structure and see if one can find a pathway from, say, a high pressure, high temperature synthesization position down to ambient conditions in order to guide experiments better how to achieve these structures. Because one thing is saying, well, this structure is thermodynamically stable and it has a high TC. The other thing is for the experimentalists to actually be able to, and I think research nowadays tries to account for that discrepancy a bit, to also trying to simulate the synthesization of these materials in the computer.
So where and what did you study, and why did you decide to go for a PhD?
So I studied here at the Graz University of Technology physics, because I've been fascinated with physics all my life. I mean, not physics, but I just wanted to understand how the world works, why the sky is blue, why certain things happen and other things don't happen. And physics was, the logical choice then as a study. And I think for me it was the right choice to do physics. And I had a lot of fun during my master project. and then decided that I would also do a PhD. And during my PhD, then I became fascinated by superconductors, and I've stayed with superconductors basically ever since.
So you didn't expect to, because now you're pretty young, but still you're already a professor, right? So you didn't expect to become a professor. You simply followed the flow, so to say, and then here you are.
Right, yes. I was taking one step at a time. I wasn't planning too far ahead. So when I started studying physics, I knew I probably want to go until finishing a PhD. But I wasn't sure whether I would try to stay in academia or I would find a research position or a similar position in a company. But yeah, one thing led to another. So after the PhD, I was granted a fellowship, which allowed me to go to the UK for 2 years. And I met very great people there. And again, I had a lot of fun doing research, and in the end everything lined up more or less for me perfectly. So yes, I'm very happy that I'm still able to do research and do those things that interest me the most in this respect.
How hard is it for you to balance your private life and your career?
At times it's difficult. So there are always up and downs. So there are phases where it's very busy at work, where you have a lot of deadlines, where you have a lot of projects, and then there is less time for family or for your own person. And then again, there are other times where it's a bit slower at work and you can take a bit more time to spend with family, with your loved ones. So I try to balance it like that in order to not only look in day to day, but on a broader basis. I think it averages out nicely. At least for me and my family, it works. And yeah.
So going back to these aspects, for example, since you mentioned having busy days at works and being overwhelmed sometimes maybe with deadlines and something, have you ever compared your situation, work situation, with some of your colleagues outside academia? Have you ever regretted not having moved to industry or something? So you're not like a stay away of academia guy if you want to preserve your sanity, right?
Well, I know a few colleagues that started studying with me, and after the master project or after the PhD, they moved into a more company environment, or they work for a company now. And it's not also only roses there. Usually the salary is very good in tech industry, and it might also be easier to enforce a strict work hours and private hours, because you do what you are supposed to do and then you stop. Whereas in academia, it's, if I'm responsible for a project, if I don't do it, nobody's doing it, right? So even if I'm above my hours, I still need to do it because the project needs to be done. On the other hand, I'm more or less completely free with my research, so I can really dig into those interesting questions or at least those that I find interesting. And I'm not held back by any requirements of some clients or what they think is the most important thing. And from what I hear from my colleagues also there, in a company, you also have deadlines. You also have projects that need to be finished, or that you have deliverables that you have to have at the end of the month, for example. So there are also times there where it's extremely stressful for them. And then arguably maybe the pressure is even higher to meet those deliverables, because you don't want to lose a very high paying customer, for example. Whereas in our case, it's papers that you need to publish. It's also grants that you need to get in order to have further funding. So yeah, I think it can be nice on both sides, but it's also stressful on both sides. So
what do you like most about working in academia, and what do you dislike the most?
That's a tough question. As I mentioned, I really like the freedom of pursuing research ideas, of doing fundamental research, trying to look behind the curtain and see how these materials work, how they become superconducting and so on. I also love being able to be in contact with similar-minded persons, with a lot of very bright people with the similar interests, and to pursue research ideas together. I think that's a great thing to have. What I like least in academia is, writing proposals, right? I mean, nobody likes to write proposals, I guess. So it takes a lot of time, and also first to write the proposal, then it's about to be reviewed, then you get the decision. So it takes a lot of time away from me being able to do other things. But then again, once you are granted the proposal, then you can do again nice research with other people. So maybe I guess also paper writing. I mean, I don't hate it, but I rather like to look into new ideas and new materials and new calculations than write something up that I already know. But I mean, of course, it makes sense to order your thoughts, to put it into a nice work that also others can then read and understand properly.
If a high school student were to ask you for advice whether or not to study physics, what would you tell them?
Well, absolutely. I think it's the most interesting study that you can do. I mean, of course, you need to want to try and understand what's happening around you. So I think if you have this interest in all the things around you, and see how the world works, then I think physics is a great study, because you get to know a lot of different fields, and you basically get an insight into many, many different topics, from theoretical physics, superconductivity, to other quantum phenomena, to more classical fields like astrophysics, for example, particle physics. So there's a huge area of things that you could do with physics. So for me, it was the right choice, and I think it's probably a good choice for a lot of people. But you also need to bring a certain amount of interest in mathematical foundations and mathematical framework with you, because mathematics is basically the language with which we physicists convey our ideas. So if you're a bit interested in mathematics and in the world in general, I think physics is a fantastic way to spend your life.
And going one level up, I guess you have to endure some kind of frustration, right? So you must be resilient if you want to stay in research.
Well, definitely. So, but again, I think it applies to many other fields as well. I mean, sure, there are frustrations. There are situations where you think, or where you doubt whether it makes sense what you're currently doing, and if you not rather do something different. But I think all the other occasions where I'm just very fascinated, interested by what we are currently what we are researching, away these phases of frustration, definitely.
Okay, I think that's about it. Thank you for your time, Christoph, and until next time, I guess.
Thanks a lot for having me.
So, thanks for listening.
And hear you next time.